Imagine plummeting toward a pitch-black ocean at 150 miles per hour, surrounded by a storm that is violently tossing a 100,000-ton steel runway in every direction. You are out of fuel, you are exhausted from a 6-hour combat patrol, and the only thing standing between you and the crushing depths of the Pacific is a patch of non-skid deck the size of a tennis court. You cannot rely on your eyes because the horizon has vanished into the darkness. You are flying purely on instruments, staring at a tiny glowing orange light called the meatball. As you cross the threshold of the ship, you do not pull back on the stick to flare for a soft touchdown. Instead, you drive the aircraft directly into the steel deck with bone-jarring force. The moment your wheels slam into the metal, instinct screams at you to hit the brakes. Instead, you slam the throttles to maximum afterburner. You feel a violent, terrifying deceleration as a 2-inch thick steel cable catches a hook on the tail of your jet, dragging your 50,000-pound aircraft from flight speed to a dead stop in just 300 feet. If the cable snaps or if the hook misses, those blazing afterburners are the only thing that will give you enough airspeed to fly off the angled deck and avoid plunging into the sea. This is the night trap. It is universally considered the most terrifying 3 minutes in all of military aviation. And for the men and women of United States naval aviation, it is just the commute home. When people look at fighter jets, they often group them all together into one generic category of sleek supersonic machines. But there is a massive fundamental engineering chasm that separates land-based Air Force fighters from the apex predators that operate off the decks of aircraft carriers. If you took an Air Force F-16 or an F-22 Raptor and attempted to land it on an aircraft carrier in the manner of a Navy jet, the aircraft would literally shatter. The landing gear would collapse, the struts would snap, and the airframe would buckle under the immense kinetic stress. Naval fighter jets are not just airplanes, they are flying anvils. They are engineered to endure a lifetime of controlled crashes. Everything about a carrier-based fighter is over-engineered. The landing gear is massive, constructed from high-yield steel and titanium, featuring heavy-duty dual-chamber shock absorbers designed to dissipate the energy of a localized earthquake. The airframe features a reinforced keel, a structural spine capable of handling the violent pulling forces of the arresting cable and the explosive pushing forces of the catapult launch. Because space on a carrier is the most valuable real estate on Earth, these aircraft must feature complex hydraulic folding mechanisms in their wings, allowing them to be packed tightly together in the hangar bay like a three-dimensional jigsaw puzzle. This added structural reinforcement, the heavy landing gear, and the folding wing mechanisms add thousands of pounds of dead weight to the aircraft. A naval fighter carries this weight for its entire life, sacrificing top speed and maneuverability compared to its land-based cousins, all for the privilege of operating from a mobile patch of American sovereign territory anywhere on the globe. For the last 2 decades, the undisputed workhorse of this brutal environment has been the Boeing F-A-18 Super Hornet, universally known in the fleet by its radio call sign, the Rhino. To understand the Rhino, you must look at its evolution. The original F-A-18 Hornet, the Legacy Hornet, was born in the 1970s from the YF-17 prototype. It was a nimble, reliable fighter, but it had a fatal flaw. It lacked range, and its ability to bring unexpended heavy munitions back to the carrier, known as the bringback weight, was dangerously low. The Navy needed a bigger, badder machine. The Super Hornet looks like the original jet, but it is effectively a completely different aircraft. It is 20% larger, carries 33% more internal fuel, and has a significantly larger wing area. It is powered by 2 General Electric F414 turbofan engines, generating a combined 44,000 pounds of thrust. The Rhino is not the fastest jet in the sky, and it is not a pure stealth fighter, but it is an unparalleled brawler. It is designated as an FA because it is a true multi-role strike fighter, capable of dogfighting enemy jets fighter, and seamlessly transitioning to dropping precision-guided munitions on ground targets attack in the same mission. One of the most defining aerodynamic features of the Super Hornet is its incredible high angle of attack, or high alpha, capability. This means the pilot can point the nose of the aircraft at an extreme upward angle while the jet continues to move forward without stalling the engines or losing control. This is achieved through the massive leading edge extensions, LEX, the broad, wing-like surfaces that run alongside the cockpit. These extensions create powerful vortices of air that flow over the wings and the twin vertical stabilizers, keeping the aircraft stable at speeds and angles where other jets would simply fall out of the sky. In a dogfight, this allows a Rhino pilot to rapidly point the nose of their jet at an adversary to take a missile shot, a maneuver that has frustrated countless Air Force pilots in simulated combat exercises. But the Rhino is primarily a bomb truck. Look closely at the wings of a fully loaded Super Hornet and you will notice something strange. The weapon pylons are not perfectly aligned with the airflow. They are visibly canted outward by several degrees. This causes aerodynamic drag, which slows the jet down and reduces its range. Why would engineers do this? Because during testing, they discovered that when weapons were released from the inner pylons, the aerodynamic flow under the massive new wings caused the bombs to drift inward, creating a terrifying risk that the weapons would collide with the aircraft's own fuselage. Canting the pylons outward ensures safe weapon separation, a brutal but necessary engineering compromise prioritizing safety over aerodynamic purity. But dropping bombs and shooting missiles is only the visible spectrum of modern warfare. The most critical battles fought by the carrier air wing happen invisibly in the electromagnetic spectrum. This is the domain of the Rhino's most crucial sibling, the EA-18G Growler. From a distance, the Growler looks identical to a two-seat F-A-18F Super Hornet, but look closer. The wingtip missile rails are gone, replaced by massive rectangular pods. The internal cannon has been removed, replaced by a maze of fiber optics, cooling systems, and microprocessors. The Growler is the Navy's premier electronic warfare aircraft. Its mission is to control the invisible battle space. Using its ALQ-218 tactical jamming receivers and ALQ-99 or next-generation jammer pods, the Growler can detect, analyze, and obliterate enemy radar and communication signals. If a carrier strike group needs to penetrate heavily defended airspace protected by advanced surface-to-air missiles, the Growlers go in first. They do not drop bombs. They fire targeted beams of electromagnetic energy that blind enemy radars, scramble their communication networks, and insert false targets into their computer screens. An enemy missile battery cannot shoot down what its radar cannot see. The Growler creates a corridor of electronic silence, allowing the bomb-carrying Rhinos to slip in, destroy their targets, and escape before the enemy even realizes their screens have been compromised. It is the ultimate force multiplier, and it is a capability that makes American naval aviation uniquely devastating. As capable as the Super Hornet and the Growler are, they are fundamentally fourth-generation aircraft operating in a fifth-generation world. Adversary nations have developed advanced stealth fighters and hyperlethal air defense systems designed to push American carriers thousands of miles out to sea. To counter this, the Navy needed a true fifth-generation stealth fighter capable of surviving the violent environment of the carrier deck. They could not use the Air Force's F-22 Raptor. It was not designed for the corrosive, high-impact world of naval aviation. Enter the most controversial, expensive, and ultimately revolutionary weapon system in military history, the Lockheed Martin F-35C Lightning II, also known as the Panther or affectionately as Fat Amy by its pilots due to its thick, bulbous fuselage, the F-35 is actually three different aircraft. The Air Force uses the standard F-35A. The Marines use the F-35B, which can hover and land vertically. But the Navy uses the F-35C, and it is a vastly different beast. To adapt a stealth fighter for an aircraft carrier, engineers had to radically alter its geometry. The F-35C has a significantly larger wingspan and a larger tail control surface area than the A or B models. This massive wing area generates much more lift at lower speeds, allowing the C model to fly a slower, more controlled, and safer approach glide path toward the pitching deck of the carrier. Because the wings are so large, they had to be designed with a hydraulic folding mechanism at the tips, allowing the jet to fit onto the carrier's weapon elevators and into the cramped hangar bays. The landing gear of the F-35C is drastically beefed up, featuring massive dual-wheel nose gear and a reinforced tailhook integrated seamlessly into the stealthy underside of the fuselage. Maintaining a stealth aircraft at sea was previously thought impossible. The salt spray, the abrasive non-skid deck, the constantly fluctuating temperatures, and the corrosive exhaust of other jets are a nightmare for the delicate radar-absorbent material RAM coatings that give the jet its invisibility. On older stealth planes like the B-2 or F-117, fixing a scratch in the RAM coating required climate-controlled hangars and toxic chemicals. The F-35C utilizes a baked-in, durable RAM coating designed to withstand the brutal maritime environment. Maintainers on the carrier deck can patch the stealth coating using specialized tape and sealants while the jet is parked on the flight deck, exposed to the elements. But the true power of the F-35C is not its stealth or its bombs. It is its brain. The F-35C is a flying supercomputer. It features an array of sensors that redefine situational awareness. The AN/APG-81 Active Electronically Scanned Array AESA radar can track multiple targets in the air and on the ground simultaneously while remaining virtually undetectable to enemy warning receivers. But the true magic is the Distributed Aperture System, DAS. The aircraft is covered in 6 high-resolution infrared cameras that provide a continuous 360-degree spherical view of the world around the jet. This video feed is projected directly onto the visor of the pilot's $500,000 helmet. If the pilot looks down at their lap, they do not see their knees. They see through the floor of the aircraft to the ocean below. If they look over their shoulder, they see through the seat to track a missile approaching from behind. The computer takes the data from the radar, the DAS, the electro-optical targeting system, EOTS, under the nose, and the electronic warfare antennas, and fuses it all together into a single cohesive picture. The pilot does not have to look at 5 different screens to figure out what is happening. The jet tells them. More importantly, the F-35C uses the Multifunction Advanced Data Link, MADL, to share this God's eye view with every other American asset in the battle space. An F-35C can detect an enemy ship hundreds of miles away, remain completely hidden in stealth mode, and pass those targeting coordinates directly to a legacy F-A-18 Super Hornet or an Arleigh Burke-class destroyer. The Super Hornet can fire a missile at a target its own radar has never even seen, guided entirely by the invisible quarterback in the sky. The F-35C doesn't just make itself lethal, it makes the entire fleet exponentially more deadly. Operating these incredibly advanced machines requires a mastery of physics that borders on the absurd. Let us break down the mechanics of the launch and the recovery. To get a fully loaded 65,000-pound fighter jet airborne from a runway that is only 300 feet long requires the application of terrifying kinetic energy. On Nimitz-class carriers, this is achieved using steam catapults. Water is boiled by the nuclear reactors, creating massive pressure. A shuttle is attached to a track in the flight deck. The aircraft taxis up and a launch bar on the nose gear is dropped into the shuttle. A holdback bar is attached to the rear of the nose gear, anchoring the jet to the deck. The pilot pushes the throttles to maximum military power or full afterburner. The entire aircraft shakes violently, straining against the holdback bar like a chained beast. Below deck, a massive valve is opened, flooding the catapult cylinders with high-pressure steam. The force builds until a calibrated breakaway ring on the holdback bar simply snaps. In an instant, the steam piston violently yanks the aircraft forward. The acceleration is brutal. The pilot is slammed back into their seat, experiencing up to 4 times the force of gravity. Blood is forced out of their brain and into their legs. They must physically brace their head against the seat and keep their hand off the control stick, allowing the aircraft's computer to maintain the precise pitch angle as it flies off the bow. On the new Gerald R. Ford-class carriers, the explosive steam has been replaced by the Electromagnetic Aircraft Launch System, EMALS, which uses linear induction motors to accelerate the jet magnetically. It is smoother, extending the lifespan of the airframe, but the physiological violence of going from 0 to 170 miles per hour in 2 seconds remains exactly the same. But launching is the easy part. Landing is where careers are made or ended. The landing area of an aircraft carrier is angled 9 degrees away from the center line of the ship. This means the runway is constantly moving forward and to the right while the pilot is trying to hit it. The pilot relies on the Fresnel lens optical landing system, universally known as the meatball. It is a complex array of lights on the side of the deck. A horizontal row of green lights represents the perfect glide slope. A yellow light, the meatball, moves up and down based on the aircraft's angle of approach. The pilot's job is to keep the meatball centered between the green lights. If the meatball drops low and turns red, the pilot is dangerously close to smashing into the back of the ship, known as a ramp strike, which is usually fatal. In naval aviation, the throttle and the control stick are used differently than in civilian flying. In a Cessna, you pitch the nose up or down to change your altitude and use the throttle to change your speed. In a carrier jet on approach, you set the aircraft at a very specific high angle of attack, AO. You use the control stick solely to maintain that angle, controlling your airspeed. You use the throttle exclusively to control your altitude. Add power to rise, reduce power to fall. It is a counterintuitive dance requiring hundreds of micro-adjustments per minute. Standing on the edge of the flight deck during this controlled chaos are the landing signal officers, or LSOs. These are experienced pilots who monitor every approach. They communicate with the incoming pilot over the radio, providing minor corrections. A little power, right for lineup, hold what you got. The LSOs hold a pickle switch in their hand. If the approach becomes unstable or if the deck pitches violently in heavy seas, the LSO will press the button, flashing red wave-off lights. The pilot must instantly abort the landing, hit full afterburner, and go around for another attempt. If the approach is good, the aircraft crosses the threshold and slams onto the deck. The A-18 and F-35 are equipped with a massive tailhook, a heavy steel bar tipped with a replaceable hook point. As the aircraft touches down, the hook bounces along the steel deck, guided by a hydraulic dashpot to prevent it from skipping over the cables. There are 3 or 4 on older ships, cross-deck pendants, heavy steel wire ropes tensioned by massive hydraulic engines below deck. The pilot aims for the 3rd wire. When the hook catches, the hydraulic engine absorbs the kinetic energy, pulling the jet to a violent halt. But the pilot cannot assume the hook will catch. If the hook bounces over the wires or if a wire snaps, an incredibly rare but lethal event, the aircraft will continue rolling off the angled deck. Therefore, the absolute first action a naval aviator takes the millisecond their wheels touch the deck is to slam the throttles to maximum afterburner. If they catch the wire, the engines roar in protest, but the jet stops. If they miss the wire, an event known as a bolter, the afterburners provide the thrust needed to launch back into the sky for another terrifying attempt. The relentless operational tempo of carrier aviation burns through aircraft at a staggering rate. The corrosive salt air eats away at the electronics, the violent landings fatigue the airframes, and the sheer number of flight hours exhausts the engines. To mitigate this, carrier jets undergo a grueling maintenance regimen. After returning from a mission, the jets must be frequently washed down with fresh water and specialized solvents to remove the salt spray. Maintainers, the unsung heroes of the flight deck, work 12 to 16-hour shifts in blistering heat, freezing wind, and torrential rain to keep these digital marvels flying. They climb inside intake ducts to inspect titanium fan blades for microscopic cracks. They swap out avionics modules in the hangar bay while the ship pitches violently in heavy seas. The lifeblood of the air wing is not just the pilots. It is the 19-year-old aviation machinist's mate covered in hydraulic fluid, troubleshooting a radar system at 3 in the morning. One of the greatest challenges currently facing the carrier air wing is the tyranny of distance. As adversary missiles push carriers further out to sea, the fighter jets need more fuel to reach their targets. Because the Navy retired its dedicated S-3 Viking tanker aircraft years ago, the burden of aerial refueling fell onto the Super Hornet fleet. In a process known as buddy tanking, Super Hornets are loaded with massive external fuel tanks and a refueling drogue pod. They launch, fly in circles, and act as flying gas stations for the other strike fighters. At times, up to 30% of all Super Hornet sorties were dedicated purely to this refueling mission. This was burning through the flight hour lifespan of the A-18 airframes at an unsustainable rate, taking high-end strike fighters out of the combat rotation just to pump gas. To solve this crisis, the Navy is currently integrating the MQ-25 Stingray into the carrier air wing. The Stingray is an unmanned, autonomous drone designed specifically for aerial refueling. It launches from the catapult, flies its programmed route, refuels the manned fighters, and lands back on the carrier, all without a pilot in the cockpit. The introduction of the MQ-25 is a monumental shift. It frees up the Super Hornets to go back to their primary mission of dropping bombs and shooting missiles, and it represents the first major step toward man-done-man teaming, where human pilots in F-35s will operate alongside swarms of autonomous drones in the battle space. The physical and psychological toll on the human beings operating these machines is immense. Flying a fighter jet over featureless, open ocean at night is an invitation to a terrifying phenomenon known as spatial disorientation, or spatial D, without visual references like a horizon or city lights. The fluid in the pilot's inner ear can play tricks on their brain. A pilot might feel absolutely certain that they are flying straight and level, while their instruments scream that they are in a steep descending bank toward the water. The pilot must force themselves to ignore their own biological senses, which have kept humanity alive for millennia, and trust exclusively in the glowing digital displays in the cockpit. Trusting the machine over your own body requires a level of psychological discipline that is forged through years of brutal training. When a pilot completes a successful night trap in a storm, shuts down the engines, and climbs down the ladder onto the pitching deck, their flight suit is often soaked with sweat. They have survived another encounter with the most unforgiving environment in military aviation. The fighters that operate from the decks of American aircraft carriers are not merely weapons. They are the physical manifestation of a nation's geopolitical will. From the reliable, heavy-hitting brawn of the Super Hornet to the electronic sorcery of the Growler, and the digital, stealthy omnipotence of the F-35C Lightning II,